Thank you for joining us for the Consulting Specifying Engineer webcast, Critical Power, NFPA 110, Standard for Emergency and Standby Power Systems, sponsored by ASCO Power Technologies. I'm your host and moderator, Amara Razgas, with Consulting Specifying Engineer and CFE Media and Technology, and I will be with you for this hour-long session. If you're having trouble with your slides or the audio, refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do a couple of system checks before contacting an online technician. If you do need help, type a message into the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, use the Event Resources tab on the left side of your screen. Please type questions for the presenters in the Ask a Question box on that left side of your screen. You may ask questions at any time during the presentation. The Q&A will start in about 45 minutes. If you're interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the Learning Unit exam and to download your AIA CES certificate, use the Learning Unit exam tab at the top of your screen. The quiz will open in a new browser window, so I recommend you open it right now because that link breaks when the webcast signs off. Only live attendees will have access to the exam to achieve credit for this webcast. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. All right, here are the learning objectives. We'll talk about these in today's presentation. Please note that any blue underlined text you see will be a hyperlink in the PDF where you can get more information. Let's now hear from this session's sponsor. At the end of the commercial, you may experience a few seconds of silence to make up for different internet speeds. Please stay tuned for the next minute. Very good, thank you. We've lined up two presenters who are really well informed on this topic. Tom Devine is a senior electrical engineer with Johnston, LLC. He has spent about 25 years in the consulting engineering field and the past several years designing and engineering healthcare facilities. Other projects include data centers, light industrial plants, and campus distribution systems. Richard Vedvik is Senior Electrical Engineer and Acoustics Engineer at IMEG Corporation. Rich has experience in the healthcare, education, commercial, and government sectors. His electrical engineering experience includes lighting design, power distribution, emergency power systems, and fire alarm systems. both Rich and Tom are a member of the Consulting Specifying Engineer Editorial Advisory Board. All right, I'm eager to get started on this discussion, but first we want to ask the audience for some input so we know what direction to take. So if you could please take this poll, I'd appreciate it. The question is, why did you sign up for this session? So if you could take a moment to give us a little bit of background information, that would be fantastic. All right, the answers are coming in here, so let's take a look. It looks like the overwhelming response is, I want to know more about standby power. So thank you so much for that information. Very good. All right, Rich, you're up first.
Fantastic. Thank you, Amara. And thank you for everybody and to everybody for signing up. NFPA 110 is a really fun topic. It's one of my favorites. But you'll notice that throughout this presentation, we're going to be talking about other sections of code. Now, I've listed some here, not to read them to you, but to remind you that you're not just looking at 110, calling it a day. You're also going to look at every applicable section based on the type of fuel you're using. And of course, you're going to have to reference NFPA 70. And there's a variety of articles within there that are going to be more specific to those different types.
Here's a list of changes in the 2022 edition of NFPA 110. First, there's the introduction of requirements for fuel cells. With these requirements in place, fuel cells can now be used as standby energy sources. Adding them to the code leads to the separation of requirements for systems with rotating equipment and those with fuel cells, and that makes for a lot of paragraph renumbering. Things that might typically be called editorial changes. They're changes to the text, but they don't change existing requirements. And Richard will talk about fuel cells later. There are also expanded requirements for short circuit and design testing. The previous edition said only that generators would be tested for short circuits. 2022 adds phase to ground, phase to phase, and three-phase bolted faults. This requirement may wind up being more interesting to manufacturers than it is to facility designers. Annex A, new paragraph A 8.3.7 has guidance and recommendations for fuel monitoring and fuel quality management. Now note that provisions in the annexes are not mandatory, but are typically informative in nature, but you may run into AHJs who want to enforce those. And finally, Annex A paragraph A56451 has expanded recommendations for replacing starter batteries for rotating equipment based on testing the electrical characteristics and on the environmental temperature rather than a strictly age-based replacement cycle.
Excellent points, Tom. Thank you. So I get a common question of when do we need to apply NFPA 110? One way you can look at it is if it's for systems that support life safety, and that if the system fails, people could die. We're going to talk about what that means from a level classification here shortly. You also might find auxiliary systems that maybe just power chillers, and maybe it's a good reference, a good idea to reference NFPA 110 for there. You also will find AHJs that are going to support that and enforce it. So you're going to have to ask them, all of them, because there's more than just one. The list I have here is not inclusive of all of them, obviously. So contact them, ask them specifically, explain your project type early, and ask them, are you going to apply and require compliance with NFPA 110, and which version? And are you looking at the annex, as Tom mentioned? Now, we're talking about 110, but obviously we're going to be using terminology from NFPA 70 as well. And as you can see, they don't exactly line up. You have the essential electrical system or energy storage systems in NFPA 70 that don't match the terminology in NFPA 110 of EPS and EPSS. Now, are they similar? Yes. And do they kind of account for the same things? Also, yes. But as we go through this presentation, we'll hopefully clear a little bit of that up for you, so you'll be more informed on when we're talking EPS versus EPSS, and when we're talking ESS versus ESS. This is fun. Now, a typical power distribution system that you might see is shown here. And we have the EPS in the green generators and the EPSS in the transfer switches. But we also have the normal service equipment in light blue and the distribution downstream of those switches shown in a variety of colors because it makes it fun and easy to see the difference in branches. Now, your specific project obviously is going to differ, but the takeaway here is that there are multiple parts and pieces in this system. And when we talk 110, we're talking EPS and EPSS typically. There's a lot of the additional building that's going to fall within NEC 70. So while NFPA 110 doesn't actually tell you the branch designations of switches, we have to look at NFPA 70 specifically for that. Now, we're going to get Chapter 6 in NFPA 110. That's going to talk to us about transfer switch equipment. But the branch designation happens in other sections. For example, if you're healthcare, your NFPA 99 and Article 517 of NEC, you're going to have life safety, critical, and equipment branches. Now, the designations and what can be on there is within NFPA 99 and 517. Conversely, if you're not healthcare, and you don't have to comply with 99, then you're going to look at Articles 700, 701, and 702. There, your emergency, legally required, and optional standby branch designations are contained within informational notes within those respective sections. And they don't perfectly match or align, so you do have to read each of those specific to your actual project. Now, you'll hear us use the terms switchgear or unit substations. What you see here is an example of what we would term the EPSS, Emergency Power Supply System. This is the unit substation, and that has transformers and also circuit breakers within the switch gear. All of this is larger than, say, a UL 891 switchboard. So you have to take space into consideration when you're laying these spaces and rooms out. This is fairly large gear. It could have been made more compact, but the owner wanted switch gear. So keep that in mind and ask that question early so you can plan for that space. In addition, I'd like to note that the depth of this gear is based on how much conduit you can actually fit inside of it. So if you want a lot of breakers in a section, you're going to need deeper gear. In this case, we went with 2 per section because we were limited on depth. And you can see there's a lot of wiring. So respect your electrician friends because they go through a lot of work to install this. Now, the EPS versus EPSS delineation is actually clarified in drawings in the back in the annex. So we have Chapter 4 for EPSS classification, Chapter 5 for EPS explanations and requirements, and then Chapter 6 for EPSS, the transfer switch portion. Now, essentially, the EPS, or emergency power system, is the generator, the accessories to make the generator work, and the circuit breakers associated with them. The EPSS, you can think of as the distribution side, and that's going to be the transfer switches and the overcurrent protection supplying the emergency side of those transfer switches. So as we use those terminologies, think of this image and, of course, reference that in the annex as needed. Now, in Chapter 4, we have 3 classifications. That's level of risk, outage duration, which is type, and runtime, which is class. So we might have a NFPA 99 requirement for a level 1 type 10 class X EPS. And that means we're an EPSS. And that means level 1 for high risk, like Tom's going to talk about shortly. Type 10 for a 10-second outage is acceptable. And class X, saying that another section of code and another AHJ has to actually tell you how long that needs to be. You're going to reference this for your project specifically, but note that NFPA 110 is not telling you what you have to comply with here. It's just listing them out, explaining the differences, and letting other sections of NFPA come back to this and tell you exactly what it needs to be.
Here's some of the requirements for the EPS location, the location of the emergency power supply itself. And we'll start with level 1. Those requirements are in Chapter 7. And here are some of the requirements for indoor. We'll start with indoor. The EPS room has to be separated from the rest of the facility, and it has to be dedicated to the EPS, and it has to have a 2-hour fire separate. Things that are necessary to maintain and repair the EPS and equipment that serves the room, things like ductwork and cooling equipment, for example, and EPSS equipment, transfer switches, any component of the system down to the load contact of the transfer switch, are permitted in the room with the EPS, but nothing else can be in that room that doesn't serve it. If the EPS is outdoor, it has to be in an enclosure that can resist snow and rain, and no foreign equipment can enter that enclosure. Ventilation, air supply, and exhaust have to come through a wall opening or a shaft, air shaft with a 2-hour fire rating. And there are no fire dampers allowed in those shafts for level 1. If the normal service equipment is rated over 1,000 amps and operates at over 150 volts to ground, so it would for us in the US be typically a 480 volt system, then no components of the EPSS, again, anything in the standby system that's upstream of the load contacts of the transfer switch, can be in the room with the normal service equipment. Normal service equipment is not defined in NFPA 110, but its definition comes from the National Electrical Code, NEC. It's the service entrance. It is entirely permissible to have EPSS components in the same room with other normal power equipment. Here are some requirements that apply to the EPS room for both a level 1 and a level 2 system. Ventilation air requirements are the same as for level 1, but fire dampers and shafts aren't prohibited for level 2. We have to have at least 36 inches around the generator, and you'll note that the generator in that photo doesn't really comply. Radiator discharge has to go through a wall opening or, again, a 2-hour rated shaft. And any louvers that are motor operated have to be spring open and motor closed, and that's to ensure that they fail open. Rotating equipment requires vibration isolators, and the EPS room has to have a battery light. And that intent is to be sure that personnel who are trying to work on an EPS that fails to start won't have to do it in total darkness. Chapter 7 adds in its Annex A paragraphs, and its paragraphs in Annex A lists some potential disruptive influences. And they're described as design considerations, and there are no detailed descriptions of exactly how they're to be addressed. Usually, things labeled design considerations are of local or regional interest. NFPA doesn't address every possible hazard. It leaves some of those issues to local authorities having jurisdiction to address the hazards that come up in their geographical areas. It wouldn't make sense, for example, to have detailed requirements for hurricane resistance for an installation in Omaha, or to prescribe earthquake mitigations in a seismically inactive area. So NFPA highlights these hazards in the standard, but doesn't prescribe specific mitigations. And that last item on my slide, noise control regulations, isn't a hazard, but it is an item of strictly local interest.
Excellent point, Sam. Now, there are a variety of types of EPS. And when we look at Chapter 5, we're going to see a lot of them listed out. But it's important to note that there are other types of standby power systems that aren't necessarily covered by NFPA 110. For example, we might be looking at electrochemical ESS from NFPA 855. And obviously, when we come back to the NEC and we look at NFPA 70, the EES can be in a variety of locations, whether we're talking about 517 for healthcare or Article 700 for emergency systems. So the point here is that you want to take into consideration holistically what type of fuel system, what type of standby power system you have, and then apply the appropriate section. And when you do have some electrochemical standby systems, like batteries, for example, you're going to have to comply with a lot of different sections of code because we're storing electrolyte, and the volume of electrolyte and the type of electrolyte that's being stored, if we're talking batteries, is going to carry with it ventilation requirements and fire rating requirements in other sections. Additionally, it's always good to note that if the supply system wants to be uninterruptible, for example, battery replacement and maintenance should be taken into consideration. So am I going to lose the entire string if I replace batteries because they all have a specified amount of life? That's for the engineer to decide. And you're going to want to take that into consideration where multiple battery cabinets can sometimes solve those problems. We're not going to go into much more detail about this precise type, but I did want to at least mention that you have other types of energy storage that are within other sections of NFPA. So if you're curious about that, you're going to look elsewhere.
And we got some pre-conference questions, or pre-webcast questions from a bunch of the listeners that loosely fall under the heading of compliance issues. And I'm going to address some of those right now. The The first is what about fire pump service? And how does that affect generator sizing? And NFPA 110 says that an energy converter has to have capacity to start and carry its loads according to its EPSS type. That means that it has to be stout enough to add the fire pump to its maximum load, or it has to have load shed to drop lower priority loads in favor of the fire pump. Now, the NEC covers fire pumps in Article 695 and makes that same statement explicitly in 695.3D. There's a popular misconception about NEC requirements for standby service to fire pumps. 695.4B2 says that the normal service to a fire pump will have an MOCP that's rated, or an OCP that's rated to carry locked rotor current indefinitely, or that it'll meet certain other criteria to hold itself closed on very high currents. So an overcurrent device served from an on-site generator, though, has to be sized according to the rules of Article 430 as if it were a standard motor. And the intent is to protect the generator from shutdown if the fire pump can't start due to excessive current, and which would leave the building without a fire pump and without egress lighting as well. The requirements for fire pump protection of emergency feeders, now I'm talking about fire protection for emergency feeders. It comes from NEC 7.10D for high-rise buildings, large assembly, and large educational occupancies. Circuits have to be protected in one of 5 ways. They have to be protected by automatic fire suppression, a listed electrical circuit protective system. They have to be fire-resistive cable, or they can be protected by a couple of structural methods. To be protected by fire suppression, circuits have to be installed in spaces or areas protected by an approved automatic fire protective system. Now, our circuits are usually installed above ceilings, while fire protection systems are usually protecting space below the ceiling, the occupied zone. It's not entirely clear whether feeders installed above the ceiling of a fully sprinklered area are considered to be in the area protected by the sprinklers or outside of the space protected by the sprinklers. In the end, an AHJ will decide, so it's important to get their opinions during the design process. Healthcare occupancies used to be on the list of occupancies in the 2017 NEC, but that requirement was amended out in 2017. NFPA 99, the Healthcare Facilities Code, started exempting healthcare from the requirements for fire protected feeders with the 2015 edition. And here's more compliance issues. Sometimes we want to add an emergency system to a building that doesn't have an emergency system. And this is not always simple as simple as it might seem to be. An emergency system is a level 1 system by definition, so no components of its EPSS can be installed in the room with the normal service equipment. Depending on how the distribution is arranged, that may mean that you have to find additional space or create additional space for the emergency system. Article 700 says that the emergency transfer switch can't serve non-emergency loads. And in a building without an emergency generator, those circuits won't be separated from other loads. In the process of adding the generation system, circuits must be identified and served from new emergency distribution equipment. For larger, complicated facilities, separating emergency loads from other loads can be expensive and time-consuming, and the cost can be difficult to explain to an owner. The same issues can arise in older facilities built before this requirement existed. In this slide is a snip from a panel schedule in an existing building where emergency and optional loads have been mingled. And there's a dozen circuits or more than a dozen circuits shown there, and only one of them serves a proper emergency load, a component of the fire alarm system. Another question, is a separate transfer switch required for Article 700 loads when an entire facility is on standby power? And the answer is yes, it is required. The NEC says that a transfer switch that serves any emergency loads cannot serve any other types of loads. There is no exception for a building that's completely supported by standby service. You might be surprised how many people feel that they can use a single transfer switch to power an entire building and that it will serve both emergency and all the other loads. That is not the case. In a lot of facilities, a small emergency system serves mostly lighting, and a much larger option will serve HVAC. And in order to get selective coordination between the optional system and a single generator breaker, it can be necessary to use a lot of smaller transfer switches to serve those optional loads. Okay, what's the difference between emergency loads and legally required standby? And those are defined in NEC 700 and NEC 701. And 700 loads require standby service either by law, codes, or the declaration of an AHJ, and they're just specifically described as emergency. They're essential to life safety. A classic example of an emergency load is egress lighting. 701 loads are also required by code or an AHJ, and they are designated specifically as legally required standby. In general, the loss of 701 loads could create hazards or maybe hamper rescue efforts. Examples of an Article 701 loads are smoke removal systems and sewage disposal systems. Now, emergency circuits, 700 circuits, generally have to be separated from all other wiring, while 701 circuits can share raceway and boxes with other circuits. Emergency loads have to be energized within 10 seconds. 701 loads have 60 seconds. The generator capacity required for both types of loads is an Article 220 calculation of the demand load. And that Article 220 calculation is the typical calculation we would make to determine the load on feeders or distribution equipment. And finally, both systems have to be selectively coordinated. Now, can natural gas be used as a fuel source? And yes, it can if the supply is reliable. There's no required level of reliability or even clear definition in NFPA 110, so normally an AHJ will make that determination. Natural gas can offer some distinct advantages. First, there's no on-site fuel storage, and that means there's no concern about maintaining fuel quality over time. And wet stacking is not a problem for natural gas generators. There are disadvantages too, like larger gas generators cannot connect within 10 seconds, making them unsuitable for emergency loads, though the industry continues to advance in that regard every year. And maybe the most important, where the same event can disrupt both gas and normal power. And that might be a seismic area, or as we had in Texas in 2019, a deep freeze, or lately, let's say, 2020 maybe, that disabled both gas supplies and electrical. When those losses are correlated, a system can't rely on natural gas for standby power. Okay, and we have a question about normal egress lighting and emergency egress lighting. Those requirements are in the International Building Code, section 1008. Normal egress lighting illuminates the egress path when utility power is available whenever the space is occupied for most occupancies. It's not, it doesn't operate, for example, in some specific spaces like sleeping units. Nobody wants the lights on while they're sleeping, or in assembly occupancy. It's not necessarily, the requirements aren't so restrictive. The minimum illumination is 1 foot candle, and with 10-foot candles required in stairways. Emergency egress lighting lights specific egress areas and some utility areas, and that includes the Fire Command Center when normal power fails. The minimum illumination is 0.1 foot candles, and an average level of 1 foot candle is required along the egress path. And there has to be a minimum to maximum ratio of 40 or less. It can't be, the difference in the brightest and dimmest areas can't be too bad. Emergency egress lighting has to stay on for at least 90 minutes. And after that 90 minutes, the level can't be less than 60% of the initial requirements.
Now, as we consider the implementation of these updated code requirements from old systems, we have to plan for outages. I get involved in a lot of healthcare facilities that have to have emergency power supply systems and EPSS also expanded. The image here, for example, is generators wanted to be larger. Paralleling gear was too small to accept larger sizes. So instead of replacing the gear entirely, we decided to laminate extra layers of busing to take it from 2,000 to 3,000, a pretty neat option. That had to be planned with the manufacturer ahead of time, but most of the planning was in the outage mitigation. Because we have to take the entire system out of service, we needed a temporary generator to replace the permanent. And those outages have to be planned out in minutes, not hours. You can't be an operational facility and not have an emergency power supply system. So you have to plan very early with all the AHJs. They required letters to the Department of Public Health because this was a hospital, and lots of plans with all the departments. Inevitably, your client's going to lose money because they're going to have to go on trauma bypass as a hospital, shut down processes as a facility. So we want to make sure that this is not a just replace in place scenario and its means and methods. The engineer of record and the designers have to plan early and often and communicate with the client all the expectations necessary to transfer from permanent to temporary and back again. Now, when we size these generators, we're going to be looking at the number of steps, the size of those steps, and inevitably it's the voltage dip and the frequency dip that's going to matter. Now, Tom's going to go into more detail in a second, but my point is you want to make sure you plan this early, because not only does it affect generator size, it can also affect the number of transfer switches. And the number and the size of those switches can affect the electrical room layouts, which your design team is going to want as early as possible.
Also, when sizing generators, of course, the main requirement is they have to be able to carry their load. They may have enough capacity to support their whole connected load, or they might be big enough for their highest priority loads and have a load shed system that drops low priority loads as necessary to keep the high priority loads on. And typically, a generator is sized with about 25% headroom to allow for future expansion or to allow for flexibility in moving loads around from one step to another. The system has to be able to take on loads without unacceptable voltage or frequency dip. Usually, the allowed frequency dip is about 15%, and the allowed voltage dip is usually about 30 to 35%, and that's actually based on when motor starter contacts are likely to drop out. The ranges for systems that serve sensitive loads like imaging equipment in a medical facility or laboratory equipment in a scientific facility will be narrower, of course. Loads typically applied in steps. Emergency loads will come on within 10 seconds, legally required standby in 60, and optional loads come on at leisure. Lower priority loads often have a substantial HVAC component, so they can be very large. And so often you'll see that the optional loads are staged on in multiple steps. So to size a generator, the first thing we do is separate the loads according to their type, things like lighting, motors, scientific equipment, medical equipment, and also by the delay from loss of power until they're energized. We separate VFD motors from across the line motors because they have very different starting characteristics, and we want to account for them differently. Now, the easy way to get this data, to get the generator size, is to give the data to a generator sales representative and just ask him to size it. The less easy way is to learn to use a sizing program and do it yourself. If you do that, it can be easy to overlook something. So if you're not very experienced, it's best to have someone review the inputs and the results. Either way, it usually is an iterative process with a lot of back and forth, and it can take longer than you might think. For parallel systems, the selection process is a bit different. You have to select the generator that comes on first. Normally, only one generator can connect within 10 seconds, and that generator has to be able to carry all of the 10-second loads. Adding more generators to the bus can be kind of a probabilistic process. It's not entirely predictable, and it takes longer than that. So the smallest generator that can be the first to connect to the system bus has to be able to serve all of the 10-second loads. For loads that connect later, the paralleling system might be equipped to send permissive signals to ATSs and let them transfer once capacity has come online, or the delays in transfer switches can be set long enough to be sure that that under any condition, the generation that is required to support that portion of the load has come available. Some registrants asked us to discuss kilowatts and kilovolt amperes. Kilowatt is a measure of power, and kilovolt ampere is a measure of what's called apparent power, and that's a surrogate measurement for current. Generators are rated in power, kilowatts or kW, and apparent power, kilovolt amps or kVA. The power rating tells how much energy the generator can deliver, and it's largely based on the engine's ability to deliver energy. Apparent power describes the alternator's maximum current, and it's based on how much copper is in the unit. For a typical generator, a kVA rating is 125% of the kilowatt rating, assuming a minimum power factor of 80% during operation. Now, when doing a load analysis for a standby system, and most AHJs do require them, it will often compare the kVA of the load to the kVA rating of the generators. That's not strictly kosher. If the load's power factor is too high, the engine may not be able to support it. It can't produce enough energy to match its kVA rating, because that's 125% of the energy it can produce. But in practice, it works. Where there are a lot of different loads, some are always off or running below capacity, and the university says that the calculated load is never reached. We got a couple of questions about calculating generator fault current, and it's typically not calculated. The fault current is based on the unit's subtransient reactance, and that is the generator's apparent impedance for a few cycles after a fault. It only persists for a very short time. It arises from magnetic fields inside the unit changing rapidly in response to the fault, and it's practically impossible to calculate analytically. Normally, it's determined by direct testing, and its value is provided to you by the manufacturer. It's worth noting, too, that components of the standby system have to be able to withstand faults on either the utility or the generator. They run on both systems at different times. The utility fault contribution is almost always larger than the generators, so the generator fault current rarely determines the fault duty for system equipment. Now we'll look at automatic transfer switches, and in response to a question, compare contactor-based transfer switches to circuit breaker-based switches. A contactor-based ATS has a conductor that moves between two contacts. It's not able to touch both contacts at the same time, so it can't connect the generator to the utility. It's also designed to be stable in one position or in the other, and never stable in between, so that it can't leave a load unconnected to either. The circuit breaker-based switch uses two circuit breakers to switch between utility and generator, and it relies on internal logic to ensure that exactly one circuit breaker is closed at any particular time. Contactor-based switches are usually cheaper, and they're often seen as more reliable. They're also readily available with multiple transition modes like open transition, closed, or maybe delayed transition. The fault current and withstand ratings are generally lower for these switches than for breaker-based switches. Circuit breaker switches have fault withstand that's equal to that of their breakers, and those can be very, very high. They're often more expensive. Some owners see them as unreliable, saying that they are stable in a position with nothing connected to the load, and they won't allow their use.
Excellent, Tom. So one of the questions that we commonly get is associated with the 3-pole versus 4-pole options that we have with transfer switches. Now, the answer is which one we choose depends on do we have a separately derived system on the generator or not. If we are separately derived, then we have to maintain two separate neutral ground bonds, and we can't bond the neutral in the transfer switch. Suffice it to say, 4-pole switches. If we are not separately derived and the existing facility has 3-pole ATSs and bonded neutrals, then we have to match that throughout. So we're going to want to take into consideration the existing facility and whether or not we're separately derived on the generator side, and we always have to remember to maintain that. Now, Tom had mentioned the NFPA 110, Chapter 6.3, requirements of parallel sets. Now, when we're planning this from a design standpoint, we want to look at how much load we're adding at each point. So Tom covered that in pretty good detail, but we wanted to follow back up with some graphics so you could see what does this look like from a planning standpoint. We're going to have a table that's going to have each of the load steps based on the generators that are being added, and then we're also going to take load shed into consideration. That's when the paralleling gear identifies it's under a low frequency standpoint and lasts for too long. That's how it knows it's overloaded. And it's going to signal for ATSs to start to drop off. So we're going to want to make sure that we, during design, plan for a certain number of steps, plan for how that load shed is going to be configured, and what loads are going to be on it. Then, of course, communicate that with your client. we had requests about testing requirements in NFPA 110, and honestly, that could be a full hour in itself. So we're going to save a little bit of time there and remind you that Chapter 8 is what tells you everything you need to know about the testing and operational requirements within this section. And additionally, the annex has logs and matrices and spreadsheets and schedules that you're going to need for both operational testing and compliance testing and maintenance. So strongest recommendation is start with those, refer to those, and then you can, of course, tweak and add as necessary.
We're going to talk briefly about just the design process for the generator location. The requirements for the EPS location are very complicated, and they run across multiple disciplines. It can be real easy to overlook something, and it can be very costly to correct those deficiencies after construction in the field. It's worth taking time to review the generator location with the mechanical design team, and if you can persuade the architectural team to show up with them as well. Mechanical types will be calculating the required airflows and designing louvers and air sources. Architects will generally be surprised at how much space an EPSS installation requires. And getting the issues in front of these design professionals can avoid omissions and conflict within the design team later on in the project.
So let's go into a little bit more detail of kind of why we care about the size of our louvers. So we know that there's pressure drop across a louver, and that louver and damper, that pressure drop is going to be based on the amount of air we need to move. So when we make generators larger, for example, we need to increase the physical size of those intake louvers and discharge louvers. Now, those previous images were actually from a project in which we were doing just that. We were adding generators to a building, and we needed to increase the intake louver size and discharge louver size. Now, we know that pressure drop occurs, and if we have a unit-mounted radiator fan, that axial fan has a maximum pressure drop that it can tolerate. So if we actually create too complex of a path with too much pressure drop, we're going to derate the generator. The same thing happens on the exhaust. The exhaust piping diameter, which is going to be under NFPA 110, Chapter 7.10, that diameter and that size is going to also be affected and sized based on pressure drop. Now, when you're doing systems like this, you might run into, if you're doing diesel, fuel oil. Now, you're going to coordinate with your mechanical engineer for your fuel oil system, and they might actually serve boilers if you're looking at a hospital that has backup. The takeaway here is make sure you eliminate opportunities for single points of failure within your fuel oil system, such as allowing for gravity returns of your fuel oil and making sure that the supply side doesn't drain back and overflow any of your tanks. Now, we know that we have a requirement for installation, acceptance, and operational testing using load banks. You can do that manually, or you can provide a load bank. And now if you're providing a load bank, you might want to look at NEC 700.3F, which is going to require a second generator connection if you only have one. That's in case you're changing the oil or whatnot. Now, you can get a rotary ATS that's going to combine both features, both a temp generator connection and a load bank connection, into the same item. So you can make the acceptance testing and operational testing a little bit easier with a load bank connection and eliminate the paralleling capability with a mechanical interlock and allow for a temporary generator connection. Plan for this early because it is obviously going to take up space.
Here's a picture of an actual generator port installation, an Article 700 port. It's, as we said, required for emergency systems that actually rely on a single generator. It has to be ready for connection without modifying the wiring, the premise wiring, and it has to have provision for generator start and stop controls. It has to have mechanical interlocks to prevent any way of interconnecting the generator and the utility. And as Richard said, the same port is specifically allowed in the code to be used to connect the generator to a load bank for testing or maintenance. And this slide shows two generator ports, one for the emergency system and one for the rest of the building. This is a whole building supported by standby project. This was actually a forensic laboratory where autopsies are performed. And they wanted to be able to support everything in the building, but we had to have two transfer switches for that. They are an off-the-shelf product made specifically for this application.
Now, Tom had talked about the fire protection sizing, criteria earlier, but we want to at least touch on a couple more things, and that is fire service elevators. They're going to have different requirements that you're going to have to coordinate with your fire department, and obviously the fire conductors, the fire rated conductors in Article 695 for your fire pump are going to have separate requirements as well. Take both of those into consideration when you're doing your rating determinations. Now, we talked about 7.2.3, which was separation of level 1 systems, but remember, that's for greater than 150 volts line to ground, i.e. 480-277 systems, and greater than 1,000 amps. So there's more to it than I just have to keep that separation from my EPSS, from my normal service equipment. There are other criteria to take into consideration, and you're going to want to discuss and plan that early. The 2-hour requirement for an EPS depends on where is my generator breakers. Maybe those generator breakers are remote and located in this room. So we could talk a lot more about that, but from a general standpoint, read all of Chapter 7 and then also refer to the difference of the EPS and the EPSS and where that difference actually lies. If we have medium voltage, we're going to take those spacings into consideration because obviously we have a lot more space associated with a 15 kV or 5 kV class gear like you'd see on the left. And we're going to want to plan for maybe a campus distribution when we're doing medium voltage. And in something like this, we're going to have large duct banks that are going to travel throughout the campus. We want to plan for future expansions. In this case, the red were new buildings on an existing campus that were cutting through the middle of all of the existing duct banks. So our new system has to plan for separate routing of both normal and emergency. Now, Tom mentioned noise, and noise is something I get a lot into. Obviously, your intake and discharge louvers for your radiator fan are going to take up physical space and cost money. It's not uncommon to see an extra $100,000 in enclosure costs and an extra 20 feet in enclosure length simply to make it quiet enough to comply with the noise ordinance. But remember, it's not just the noise ordinance to the neighboring properties. It might be FGI compliance with noise into, say, patient rooms or occupied spaces in the building. So we want to take that into consideration because even NFPA 110, 7.6 says, be aware of noise. And last but certainly not least, we have annunciation requirements in Chapter 5 and Chapter 6 for the EPS and the transfer switch equipment. Now, on the left might be the local annunciation, and on the lower upper right, I should say, and on the lower left would be the remote generator annunciation. Now, those beautiful enclosures are going to take up space in an occupied space, and usually something that's continually occupied and attended, because we want those alarms to be known and heard. Now, there's a variety of other requirements for annunciation in both Chapters 5 and 6 that you can coordinate, and it's going to vary based on the level of your system. All right, now let's move on to the second portion of this presentation.
Exactly. Thank you so much. That is a ton of information. Thank you, Tom. Thank you, Rich. And before we get to the Q&A, we're going to want some more feedback from you. So here's our next poll. What is your role in electrical and power systems? So if you can give us a little bit of feedback here, we'd greatly appreciate it. What is your role in electrical and power systems? And as we are waiting for the audience to supply information, we're looking for a little bit of feedback from you. Oh, interesting. Okay, not too surprising. The vast majority of folks here on this presentation today are electrical engineers. So fantastic. Thank you so much for that information. So as a reminder, you can earn one AIA CES approved learning unit for this event. You do need to pass a 10-question exam. That learning unit exam tab will get you to the learning unit exam and all the information you need about that. Only live attendees will have access to the exam to achieve credit. So let's take some questions. Please type your question into the Ask a Question box, typing the presenter's name before your question so I know who should ask it. We'll get to as many as we can today in this conversation. Questions that we don't get to will be answered in writing online at www.cscmag.com. And to download the presentation slides, please use the presentation or the event resources on the left side of your screen. All right, Rich, this first question goes to you. On some recent projects, the design engineer included EPSS components In the same room is a large normal service equipment. The indicated NFPA 110 is a standard and not a code, so the design is not required to meet the requirements of NFPA 110. What are your thoughts there?
So we talked about this very early on, is when is NFPA 110 enforced? And as I mentioned, it's going to be enforced by the AHJs. This is not an enforcement by the engineer of record, but all of the AHJs that are going to be looking at that system. And if we're talking about a level 1 system that actually qualifies under level 1 under, say, other sections of NFPA that reference back to NFPA 110, that's essentially how code works. If it's referenced by another code section and it's a level 1 system, then we're going to be using NFPA 110 as the standard for our design. And of course, remember that if we're talking about separation of normal service equipment, we do have the Chapter 7 requirements of what exactly that means. Not just level 1, but also it comes into consideration with the voltage and the amperage. Is it a good idea? Absolutely. Failure of normal service equipment can be catastrophic, and we don't want to take out the emergency service equipment because we're vaporizing metal just simply 3 or 4 feet away.
All right, thanks for that clarification. Tom, this next question is for you. If you have a generator that is standby for the entire building, is it acceptable to have an inverter backup to emergency circuits such as lighting or fire alarm, and not to have a separate transfer switch?
Thanks, Amara. And I will say, I believe that it is. That's how I read the codes. And I have a project in the pipe right now that will call for a single transfer switch supporting a building and egress lights to be supported by unit equipment or battery-powered fixtures. As I see it, the requirement is that there be an emergency power source, and that doesn't have to be a generator. It can be the batteries in the unit equipment, or it could be batteries in, say, a lighting inverter.
All right, got it. Thank you. Rich, next question's for you. Does the 10-second start time apply to temporary generator connections for maintenance under NEC 700?
Absolutely. What a great question. So we know that when we connect the temporary generator, we also have to include start conductors and any of the alarm conductors. It's not just the power. So when we run on temp generators for either maintenance for, say, a couple hours, or for like the outage mitigation examples that I showed you that might last several months, we need that generator to respond just the same as the permanent generator. So you're going to have start conductors, you're going to have alarm annunciation. And another question I commonly get is, how do I provide annunciation to this temporary generator? Those are questions you have to have with your AHJ regarding how much time you're going to be using the temporary generator, how it's going to be monitored, what the type of facility it is. Are you doing it when it's occupied or unoccupied? All of that could factor in. But we want to make sure that it's a backup to our permanent installation, and it isn't exempt from the starting times that our permanent installation has to have.
Okay, thank you. Tom, next question here. Where generator paralleling breakers fail, where they fall, is that EPS or EPSS?
My reading of the code and my interpretation of the diagram that comes in the code, I'm going to try and find that from Richard's slide, and I probably not going to find it fast enough. But the diagrams that I've seen show paralleling gear as part of the EPS. It's generally seen as part of the emergency power system and not as part of the EPSS.
I would concur with that, Tom. The diagram and the nomenclature within 110 seems to very clearly identify that the breakers for current protection for the generators are part of the EPS. So that would be EPS designation, and their placement would have to comply with EPS locations.
All right, this is kind of a hot topic, Rich. Here's another question about this, a related question. We encounter AHJs who mistake the EPS and EPSS and require rated rooms for the EPSS. Have you had similar experiences, and how do you overcome this?
Well, the diagrams themselves, and really probably the first thing to do is look at the annex and show the AHJ in the annex where it clearly defines the separation between the EPS and the EPSS. And one of the points of clarification is the bus itself. So if I have paralleling gear, I'm saying that the breakers for the generators are EPS and the breakers for the serving the ATS or EPSS, but obviously the bus itself is part of EPS, so therefore it would have to be in that rated room. So the placement of that actually really does matter. Now, the clarification of if I have unit mounted breakers and I'm serving a remote bus, there it gets kind of fuzzy. I would say that's more EPSS is the bus and EPS is the breakers. So there's a variety of diagrams within the annex that you're going to want to reference when those discussions come up. But again, like we said at the very beginning, you got to have this conversation very early. Every AHJ has a different interpretation of how they see this code being applied. So ask them early. Don't ask for forgiveness. Always ask for permission. Communicate with them, befriend them, and realize this is a team effort.
Ask early and ask often. Got it.
Marlon,
thank you.
I'd like to add to that one of the things we do when designing these kind of systems is try and anticipate all of the things that can go wrong. It's a lot of trying to look forward and see things that can go wrong, find single points of failure, and back those things up. And that same thing is true of the design process. We need to look ahead and see what kind of things can go wrong in terms of interpretation of code and do something about those things early with the AHJs.
Got it. Thank you. Tom, I have a clarification question for you. You talked about level 1 for EPS, but what's level 2?
Level 2 is defined in the code. Level 1 is defined as a system whose failure could endanger human life. And I'm probably not quoting it very precisely, but that's essentially what it means. Level 2 definition is a little bit more fuzzy in that it is a system whose loss is not as serious as the loss of a level 1 system. So in general, we tend to think of it as it could cause serious injury or injury to human beings.
All right, thank you.
That's correct. And I'll add to that, too, that you'll find other sections in NEC and other sections in NFPA that will reference the requirement for a level 1 or a level 2. So which one you need is defined by other sections in other codes, and then you refer back to 110 for what you have to do.
Sure. So you both have experience for this next question, so I'm going to pose it to both of you. And Rich, if you could tackle this first. As an AHJ for healthcare facilities, this person sees many level 1 and 2 type 10s for hospitals or some sort of medical facility. During monthly load testing, some facilities cut power by manually shutting the ATS to run the generator at load. This person has suggested this is not the best way to test the system, and you're not allowing the ATS function itself to be tested within the system. Do you agree? Do you disagree? Or what has been your experience here? Rich?
Sure. This is an excellent question. And testing ATSs is important. I once had a facility that was using the test switch to test their ATSs for multiple years with no failure. And then the moment they had an actual outage, the system didn't function because there were programming errors and nobody had done a blackout test. Now, there's a difference between the commissioning test and the monthly testing. Obviously, the ATS sees things slightly differently if we flip the test switch on it versus we actually open the normal breaker serving that and truly simulate an outage. The same is true if we actually remove normal power from the generator room and the EPS room and the EPSS room entirely and see how those systems behave, making sure we don't have programming errors that would say, if the battery charger loses power, inhibit generator number 1. So we want to make sure that we test these systems entirely upon commissioning. And my recommendation to my healthcare clients is that you don't want to be surprised when you have an actual outage. And I know that blackout outages, not total blackout, but controlled, individual ATS controls, maybe just the central plant, maybe just the EPS room. You can plan that out ahead of time, and that'll give you an opportunity to see what will actually happen. What do you think, Tom?
If my memory's right, the code tells us that we have to initiate a monthly test from a different transfer switch each time until we've gotten them all. But I think that's entirely to prove that the start circuitry is still intact and that the transfer switch does have the capability to start the generator. I prefer to see that there is a blackout test done at some time. In general, though, it's very difficult to perform those in occupied facilities when you do a renovation or add a branch or add a transfer switch. So it can be challenging. I know in the commissioning of a hospital that if when the building is first built, we do blackouts. After that, the blackout test is not required.
Well, thank you both for that. I would like to wrap up today by thanking these terrific subject matter experts, Tom Devine and Rich Vedvik, for sharing their extensive knowledge of NFPA 110. And we do have one final poll. A couple of questions will pop up on your screen as soon as this webcast ends. Please take a few seconds to answer them. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, thank you for joining us. And we'll see you again at the next education session. Goodbye.